Now we come to the interesting part of this course, which is about the partial measurement. We have seen so far the total measurement, which is about the collapse of the state function to end up in one situation only or one outcome only. So the superposition of the several situations and the many outcomes will end up be in one outcome only after the measurement. So the state function has collapsed to a single result, basically. So the superposition is no longer there. So let's see then the following example. If we have a 2-qubit quantum computer, both initialized in the ground state, so we have the state will be ket 00. If we apply to Hadamard gate, then we end up having two superpositions. We have the superposition for the first qubit and the superposition for the second qubit. And as you see here, we have a superposition for the first and superposition for the second. So this is a result of applying the Hadamard gate on both qubits. So we have h times h acting on 00, and this is what we get as a result. Now, if we look, we find this is the coefficients of the states. We have the state 00, state 01, state 10, state 11, and these are the coefficient next to every state. Now, how the partial measurement is happening? So now let's assume we wanted to measure the first qubit with a measurement operator or an action operator called the Q0. So PQ0 is a measurement operator to measure the qubit. And let's imagine that to measure this qubit, we wanted to measure it and define the probability to find this qubit in 0 state. So we wanted to measure the first qubit, this one, and we don't want to measure the second. So we wanted to leave it still in quantum state. So this is like a partial measurement. We are doing it partially. So if this is continue here, we are gonna have here our measurement. So that will act on Q0, Q1, which will give us P Q0, 0 tensor product of I acting on half ket 00 plus half ket 01 plus half ket 10 plus half ket 11. So let's assume when we do this measurement, we are gonna find the qubit Q0. Assume we are gonna find it in 0 state. Then this partial measurement, what it will do, I will get Q0, Q1, a new state where Q0 equal to Q0 equal to 0. We write it in a clean way. Then I have Q1. This one will end up having half. So when we measure it and find it in 0, all situations or configurations where the first qubit is 0 will stay. And because this is now becoming a definitive of information for us, and the rest will disappear. So this one, the first qubit is 0. So we have two situations in which the first qubit is 0. And situations where it was N1, this one will be ignored because this one will be destroyed via the partial measurement. However, when we measure the first qubit has a definitive value, however, is still in the superposition. So that what we end up having. So the first one is in definitive, the second one is in superposition. Now we have performed the partial measurement. We would like to check the normalization. Is this function normalized? The answer is no. So we have to renormalize it. After the renormalization, we are going to end up having 1 over root square of 2, 0, 0, plus 1 over root square of 2, 0, 1. Okay, we could have measured the second qubit. If we measure the second qubit, we are going to do the same. So we are going to have our identity O times P of Q1, the second qubit. And then we can say, okay, we can assume any value of this one. So we can make it on Q0, Q1. Then that will be I O times P acting on half ket 00 plus half ket 01 plus half ket 10 plus half ket 11. So we have two outcomes. Assume Q1, we found it to be in the 0 state. Then all situations where the second qubit is in 0, which this one, that will stay, the rest will vanish, because now we know for sure that the second qubit will be 0. So the superposition of this qubit has disappeared, and then we are left over with the superposition in the first qubit. Then Q0, where Q1 is 0 prime, that will equal to half 00 plus half 0 1 1 0. Then we have to renormalize. Then we have 1 over root square of 2 get 0 0 plus get 1 0. We can also check the other one. Assume q1 we found it to be in one state. Then we have q0 prime q1 prime equals 1. This would equal to half. Of course, now we are going to end up with different situations. We are going to end up with these two situations. We are going to end up with half get 0 1 plus half get 1 1. Then after the normalization, we have 1 over root square of 2 get 0 1 plus 1 over root square of 2 get 1 1. So we did a partial measurement. The whole system didn't end up in one situation. We still have a superposition for the first qubit. So we have measured the second. We can find it in 0 or in 1. So that's fine. This superposition of this particular qubit has collapsed. And then we still have the superposition of the second one. So we can see here this tracing. And of course, you need to be mindful for the normalization. You have to be careful that when you do any partial measurement, you have to renormalize again. So far, we have seen the partial measurement and the total measurement. We have seen everything we need to construct a simple quantum algorithm. Now, in the next video, we are going to see the Bloch sphere, how to represent the state of the qubit visually on a Bloch sphere.